there are several ways of combining them actually. So do I want to do that? So this one works, right? This one works. It's less robust than the bisection method in certain ways. So one way we can combine these two methods is that instead of doing a bisection by looking at the middle point, we take our 2 points and then we figure out where the 0 should be if the function was a linear function, and then we do the bisection. Instead of doing it equally, we do it at the point given by this method. That's one way. We could use these two methods together. But you don't gain much robustness this way. Okay, so the question now would be, what do you do if the secant crosses the x-axis outside your interval? And that couldn't actually happen. Yeah, it couldn't happen. There's a problem with that. This secant thing is not necessarily good if the 2 points are really far away and the function curves a lot. So we might think about that next time. How do we use these two methods together? Because there's an obvious way in which you don't let them interact at all. There's just, you start with the bisection with a really big interval, and you do your find root inside of that interval, and whenever you're supposed to go outside of the interval, you bring yourself back inside. So the bisection sort of every step divides by 2, so you know that after n steps you've divided by 2 to the n, but at the same time you have this secant, that's how we call it, the secant method, this thing, which when it works it's pretty fast, as it turns out. So you have something inside, and like it might do something stupid, and then you just go to not a number, but instead of going to not a number, you fall back to the bisection for this step. But for the secant method you have 2 points, so you couldn't. Okay, this way I just described is a way to make this method, the secant method, more robust, because it doesn't go to infinity. and you don't necessarily have to um, start with a small bisection interval. You can start with a really big bisection interval, and with the two x1, x0, and x1 pretty close to each other. The other way, which is you sort of do them in parallel, you do the bisection and you use the secant method to find where to bisect, where to cut your interval in half. You cut it unevenly, and that's like a way to maybe make the bisection faster. But again, it's not guaranteed to be faster, and if it's not working properly, it will probably be slower, because when you cut in half all the time, it's the biggest interval that remains is always it diminishes by 2 to the n, right? Both intervals all the time diminish by the same amount, so it doesn't matter. If you're using defined root and you're very far from the real zero, well, it might happen that you're only reducing the size by 1% all the time, instead of 50% all the time. So it's one of these things, you probably would have to try it and see what happens. So these methods for finding roots are good to keep in mind, because you can combine them and you can add a bit of extra logic to make them really robust. You can make them as robust as you want, it's just they become more complex, and when you don't need the extra robustness, they can lead to slower code in certain circumstances where it might matter. So I think that's it for today. Firefox seems to be ready to install, which is great. Nothing like a new installation of Firefox to make my day. Let's see if there are any questions. So you see, these methods aren't particularly exciting, but they're still interesting in the sense that before you saw these methods, it's not really obvious how you find the roots, you know. Maybe the method you would use would be just to draw a picture and try to figure it out yourself. But you can't do that like 10 million times a second, right? If you need to do that on a very short time scale, then you need to dumb it down a little bit. You can't look at the function everywhere. You have to look at it a bit like if you have a mountain chain and on the mountain, but you're blind. You can only you just know the current height. But sorry, not good with analogies. So, or there's a sand hill and you're an ant and you don't see very far. Maybe you see a little bit of the surrounding and you remember where you were before, but you can jump from place to place and you're trying to find a specific height. In this case, 0. So it's interesting how you measure the speed, right? How can you predict the speed of these things? Well, depends on the scenario. For instance, maybe the function f is expensive to compute compared to the rest of this procedure. If that is the case, then it's pretty easy to optimize for speed. You know, say the function f takes 100 or 1,000 instructions. Let's say it takes 1,000 instructions. Then you have, every time you call f, you can do 1,000 instructions, or say you can do 1% of f every time you call f. You can do 10 instructions every time you call f, and the 99% of the time is spent in f. So when f is bulky, it's easy to be, you know, smarter and be optimal, because the speed is basically, up to a good approximation, it's just equal to the number of times you call f. That's the time it takes. So if you want to minimize the speed, just call f less often, right? So if you have an iterative method, then if you reduce the number of iterations, you might reduce the number of times you have to call f. If you're smarter than what we did here, you know, here we call f 1, 2, 3 times every iteration, and yet on average, you know, if you do 10 iterations, you've only gone through 11 points. So really, you can simply call f 11 times and remember the result, and let that carry through to the next iteration. And if you do that in a smart way, you can actually, unless you're only doing a very small number of iterations, but say you're doing more than 3 iterations, then you can basically call f once per iteration on average. So if f is bulky, that's a thing you might want to do that will give immediate yield in speed. All right, that's all for today. Thank you for coming by, and I hope it was helpful. If you have any questions, feel free to